This is video 2 of a 4-video playlist. In the first video, we set out the problem and described what these terms here are. And in this video, we're actually going to derive a differential equation, the differential equation that comes about because of magnetic braking. And we're going to start with a conservation of energy equation and then do a lot of substitutions, and that'll give us our differential equation. So again, the basic situation is this. We have this wire loop moving into the magnetic field. It has an initial kinetic energy, has a mass and a velocity, so it has a kinetic energy. As it moves into the field, that kinetic energy is translated first into a current in the wire. That's because of the Lorentz forces. And that current generates heat in the wire. So we have kinetic energy being translated into heat energy via electricity. And that's where we're going to get our equation from. So let's start by looking at the energy, the heat energy generated by the electric current. So we're going to look at a small element of work or energy, dW, and P is the power at any point in time. So if we look at a little increment of time, P times dt is the work done in that interval of time. And that's heat energy. So that's a small element of heat energy being generated in the interval dt. Now that heat energy comes from the kinetic energy, from a diminution or a lessening of the kinetic energy. The wire is going to slow down because of the magnetic braking, and the kinetic energy is being translated into heat energy. So we can express that same element of energy in terms of kinetic energy concepts. It's going to be the force times the distance that it travels in that small interval of time. There's just a -1 here. That means we got to stick a minus in there, and we'll see why in a second. But really have to stick a minus in there because the acceleration is negative, and the power, the heat dissipated, we're just expressing as a positive concept. So the best way to think of this is that the kinetic energy plus the heat energy has to add up to 0 because the conservation of energy principle. So that means one has to be the negative of the other. We're going to get our equation by just taking these two elements and setting them equal. So let me beat a dead horse here. This side is kinetic energy. This side is heat energy generated by the electric current. They have to be equal because one is responsible for the other. The slowing down of the wire gives rise to the heat being dissipated. Now we're going to just start substituting. And what F is mass times acceleration. And remember what acceleration is, just x double prime t. So that gives us that side. Now let's look at the electrical side of the equation. The power is I squared R. Make that substitution. And I is the voltage divided by the resistance. And voltage is the same as EMF. So let me undo that again. We have I squared. That's why we end up with an EMF squared when we make that substitution for I. All right, and now here is the real, the physics of the situation. What is EMF? EMF is given by the rate of change of the flux with respect to time. And what is that? Well, we go over here. These are all equations or formulas that we derived in the first video, so I'm just substituting now. The change in the flux is governed by how fast the wire is moving into the magnetic field. In other words, it's governed by this x prime of t here. That's where that comes from. All right, now we're almost ready to go. We want a differential equation here. I've got these differentials, dx and dt. Let me get rid of those in the following way. I'm going to take this dt here. I'm going to put it up in my auxiliary slot up here. I'm going to tee it up. Control T will put it up there. And then I'm going to divide both sides of the equation by that dt. The reason I do that is because now I have it on this side over here, and dx dt is just the velocity, or it's x prime of t. So let's make that substitution here. Actually, let me do it like this. I'm going to take this dx, and I'm going to move it. I'm going to take the dx, and I'm going to move it over here. Now that's dx dt is just x prime of t, so let me make that substitution. I do that with my substitutor. X prime of t. Notice these numbers are the same here. That's a pretty solid indication that I'm not doing anything stupid here, that is a valid substitution. So let me do that. All right, then I look at my equation one more time, and I notice I have an x prime of t here, and I have x prime of t squared here, so I can simplify this thing a little further if I divide both sides of the equation by x prime of t. So let me do that. I put it in my auxiliary slot, and I divide. All right, now we definitely have a differential equation. Notice we have x double prime on this side and x prime on this side, and all the rest are constants. So this is a fairly simple differential equation, but let's manipulate it a little bit, see if we can't simplify it even more. First thing I'm going to do is put everything on one side. I put everything on the left-hand side. I do that by clicking on this little operation here. Now those negatives, I'd rather see positive, so I negate both sides of the equation. Notice this 1 down here. This 1 says, yes, the equation so far is true. You haven't made any mistakes. So we'll kind of keep our eye on that to make sure we don't make a mistake in our equation manipulations. All right, now what am I going to do next? Again, I'm just manipulating the equation. I'm going to take this m in front of the x double prime. I'm going to tee that up and divide both sides of the equation by m. I had an unruly student there. I had to send her to the principal's office, but I think we'll be okay now. All right, where were we? We're manipulating this equation. I want to take this x prime of t. I'm just going to move it over to the left, to the right a little bit. And I do that so that I can focus on this thing here. This thing that I'm highlighting now, those are all constants. Those are all givens up here. And I could leave it in my equation and solve my equation with that in it, but it's easier to give that a name and not have to type it out over and over again. So I'm going to call that K. Let me do that with my replacer. Control L. Why L? Because R, E, P were already used, so I had to use Control L as my replacer module. And I call that K. And notice over here again, my numbers are the same, so yes, I'm remembering correctly. That's what I called it. Let me make that substitution. And let me save that to the next. All right, this is a differential equation. A pretty simple one. I'm not going to derive the solution here. I'm just going to state it here, and in the fourth video, we'll actually derive it. Anyone who's worked with differential equations will probably see pretty quickly what the solution of this thing is. Let's actually look at it. The solution is up here. This is the solution right here. That's x of t. And even though we're not going to derive it, we can test it. And how can we test it? Well, we've got x of t. We've got x prime of t, which we just got by differentiating this x of t, and we got x double prime of t. So we can just substitute those into this formula down here in our big slot. Get rid of my helpers. If I substitute x double prime of t, that is this thing, for this, and x prime of t for this, and it comes out to be 0, then I know I've got a solution, even though I don't quite know how I got it. I know it's a good solution. So let me do that. I can do that by just dragging and dropping. And then I do it with this one too. And what's going to happen quickly, it's going to disappear before you know what happened. Boom, they both went. It happened so quickly I almost don't know what's going on. So let's do this. I'm going to put a group around this thing so the program will not recognize it immediately for what it is, and it won't do the collapsing so quickly. All right, so I'm going to then substitute. I got x prime of t in there. I'm going to substitute that in there. Notice what happens. We have a k squared here, a k squared here. We have a c2, e to the minus kt, e to the minus kt with a minus in front. So if I get rid of these, if I sort of expose this piece, it will collapse it into 0 equals 0. That says that we do have a solution. This x of t up here, which I just gave you without showing you the derivation, is a good solution. And again, we'll derive it in a separate video. The derivation is a mathematical exercise more than a physics exercise, so I'll set that aside for later. All right, what are C1 and C2? In the world differential equations, they are arbitrary constants. No matter what C1 and C2 are, that formula will satisfy the differential equation. To determine what C1 and C2 are for our specific case, we have to go to the initial conditions. So let's look at that for a second. How do we determine C1 and C2? First of all, let me just write down our formula here, x of t. Let me just big that. And now I want to actually convert it into its pieces there. So that's my formula for x of t. And I don't quite know what C1 and C2 are yet. As far as the differential equation is concerned, they could be anything. This equation or this formula would satisfy the differential equation. But if I wanted to satisfy my initial condition, C1 and C2 have to be something specific. So to figure out what they are, we just do the substitutions. We're saying that at time t equals 0, x is 0. So if I plug this initial condition into there, when t equals 0, this thing becomes 1. So I just get C2 plus C1 equals 0. So let's do that substitution. The program will know from the fact that this the text element has an IC in front of it. It'll know what to do. It'll evaluate that initial condition. So that's my first equation. Let me save that. Now I undo this to get my general equation back. And now I'm going to substitute in my second initial condition. And that says I got to take the derivative of this function with respect to t and evaluate at 0. If I differentiate C1 with respect to t, it's going to just be 0. This is going to throw out a k. So watch what happens if I do all that. The program will do that for me. It ends up to be this. So let me save that. So I have two equations in two unknowns. Remember, k is known. It's just made up of the b's and the m's and whatever. It's the C1 and the C2 that we don't know at this point. So we got two equations. We can solve it. Now the first one, what's C2? That's easy. We're just going to bring up our ops again. We're going to tee up that C2, put it in our auxiliary slot, and then solve for it. So C2 is V sub O over K. V sub O, we know, That's our initial velocity, and k is a conglomeration of things that were given to us initially. So let me save that. Then we go back to this, and we big that. And now we make the substitution. We know what C2 is, so let's plug that into this formula, and then solve for C1. So I'm going to tee up C1 and solve for it. So C1 is that. So now I know what all the pieces are of my equation of motion. I know what x of t is. And as I said, we could have gotten along without defining the C1, C2, and K explicitly, because we could just substitute for them. Like if we substitute for the K, that's that. C1, that's that. C2 is that. Same formula as before, it's just a lot messier that way. So these are just, we define these constants for the sake of convenience. This is our differential equation. Let's look again at what it means. Here's our graph of that differential equation. At time t equals 0, the red line is the velocity, started at 10 meters per second, and because of the magnetic braking, it's decreasing. It never really reaches 0, and you can see that from this x prime of t is this exponential formula. So this part here, let me bring this up, we'll look at a little detail. You know, it never really gets to 0. It's just that this piece here gets very small as t gets bigger. Let's actually look at that. If I highlight this part here, right now that value is 0.47. That's when t is here. As I move t out, keep your eye on this over here. I'm going to click over here, and it becomes much smaller. As I move t further, that thing is shrinking and shrinking. So the derivative is going down. If I put my t way out here, it's very teeny. But it never goes completely to 0. It's always some slight positive number. And what about x of t? Well, that's the blue line here. And the way to think of the blue line, let's bring this up again, it's C1, which is 100. C1 is 100. So that's an asymptotic approach line, or that's the line that the blue function is approaching asymptotically. And this quantity here represents the difference between the 100 and the blue line. It's a negative number. So the C1 is 100, and then you add this negative to it, you get the blue line. Let me put this over here, put my t over here. And so we're saying that the negative piece is 36, so it's 100, which is our asymptotic line, minus 36 gives us the 64 that we have if we look at the whole formula. Now, notice what this is saying. This is saying that it will take about 50 seconds for this thing to slow down almost completely, and it'll take 100 meters for it to slow down. So that means in terms of our initial picture, let's look at this. This B field has to be 100 meters long. And this side here, the top side or the bottom side, has to be at least 100 meters long also. If either of those wasn't true, then let's suppose that this was only 1 meter long. Then after a short amount of time, the wire loop would be completely in the field, in the B field. There'd be no more change in the magnetic flux, so there'd be no more braking. So it would just continue along at whatever velocity it had reached at the time that it completely entered the field. If we want to make it shorter, we're going to have to and we want it to stop, we're going to have to change our resistance. The reason that this is not breaking quickly is the resistance is so high. Got this thing up here. This is so big that there's very little current. And since there's very little current, there's very little Lorentz force pushing the wire back. In other words, there's very little deceleration. If we decrease this resistance, then it's going to break. The breaking will be a lot more pronounced. For instance, if this were a copper wire, then the resistance would be closer to this. It's 10 to the minus, or 10 to the fourth smaller. I have to multiply it or divide it by roughly 10 to the fourth. That would be a typical resistance for just a copper wire. Now, notice what the graph is for the motion then. Here, the velocity approaches zero in about, roughly, what is that? That's 5 milliseconds. 5 milliseconds. And it reaches its stopping point in about 1 centimeter. All right, yeah, that's the asymptote that it's approaching is 1 centimeter. So, the resistance makes a big difference in the magnitude of the motion. The shapes are the same. Still this reverse exponential shape, but things happen a lot quicker and over a lot shorter distance if you have a low resistance. All right, that's enough for this video 2. In the next video, I will derive the same differential equation, that is this thing here, but I'm going to approach it via the Lorentz force.